to the channel. It's the Craven Bookworm, and today I'm going to be giving you some textbook recommendations, a much requested, you could say, topic, specifically for general relativity and cosmology. Ever since I made the video about my top book recommendations for cosmology, some people have been wondering what are some textbooks that I would recommend, because I promised in that video that at some point I will talk about some textbooks related to these topics. And since I have at least dabbled into quite a few of these, I felt like why not make you some suggestions in terms of general relativity textbooks as well as cosmology. Now, a quick note before we start is that with textbooks, contrary to regular books, I have not read all of these things cover to cover, because textbooks are frankly much tougher to get through completely. Of course, you can still go through them, and as a matter of fact, the first book that I'm going to be talking about is one that I have almost gone through completely, but it is not as easy, you could say, with textbooks in contrast to regular books. But so I'm just stating that so that you know that if I'm being very honest, I have not read all of these things in their entirety. I've mainly read bits here and there, some more than others. So I want you to still keep an open mind when you hear these suggestions and know that they're just suggestions basically, and not like you have to get these books. But without further ado, let's jump into it. And the way I'm going to kind of segregate this is by, similar as to the other video I did on cosmology, I'm going to have a section of easier, you could say, textbooks, intermediate level textbooks, and more advanced level textbooks. And even so, within all of these three, you could say, segregations, I'm going to also split it between general relativity or GR books and cosmology books. So let's start with some of the easiest ones, and let's start with GR. Now for GR, of course, the book that has been, you could say, my favorite physics textbook, at least for the past 2 years or so, is the first one that I would recommend. And I'm, of course, biased, but it is really a good book. And that is Covariant Physics by Muattas Imam. Now, if you've been on this channel before, you've seen me talk about this at some point, especially when making videos about relativity, or even the video I made recently about Kaluza-Klein theories. I borrowed a lot from this book because this book is simply amazing. The reason I like it so much is because it starts out very slowly by introducing you to concepts, and it assumes no further knowledge than multivariable calculus and linear algebra. Like, if you know these two things, you're good to go. Like, you can pretty much learn from this book from the get-go without anything else. And I love it because the first chapter so nicely introduces you to things that you may have seen already. For example, like multiple integration, where you have to kind of sometimes change, for example, from Cartesian to spherical coordinates and stuff like that. So it reviews stuff like that, and then kind of ties it into the more compact language of tensors eventually. And same thing with linear algebra. It ties all of these things together and introduces you, especially in chapter 2, to tensors. And pretty much, if you read the first 2 chapters of this book, I think you are ready to go for especially any undergraduate general relativity, you could say, course. It's amazing. It's a great one, and even shows you how this language of using the covariant formalisms in physics kind of goes into not just things like special and general relativity, but also classical mechanics and other branches of physics that you may not immediately think of before. And it's incredible. And the last chapters even introduce you to some very cutting-edge ideas at the simplest manner possible. So cutting-edge ideas in both physics, like modified theories of general relativity, as well as some of the mathematics you need to kind of work with these things on a higher level. So differential forms and things regarding differential geometry. So it's a really nice introduction to high-end, you could say, formalisms in both GR and, you could say, physics, like the mathematics you need for working with these things. So I cannot furthermore recommend Covariant Physics. Really, it's a great way to start. Now, the second book recommendations I have is one that I don't own physically, but I have gone through at least some chapters because it's the book that my university used for the course of general relativity. That is Gravity by James Hartle. And Gravity is a pretty decent introductory book. It is a book that tries to especially put emphasis on physical, you could say, intuition. So really, a lot of chapters kind of aim to bring you from your physical understanding of special relativity to start thinking about non-inertial reference frame. And it does so very smoothly. So it is a great one for kind of having a lot of thought experiments and thinking more about these things. And some of the problems in the book especially are really nice. But the one con with it, I would say, is that it is not something that introduces you to the math of GR right away. It takes its time, and you do eventually get to tensors and stuff like that, but really you get so when you're quite a way through, around the middle or so of the book. And even to quote what one other YouTuber which I saw was the Silence Asylum in his video right here, which I heavily recommend you check, by the way, because he's more authoritative than I am, and he made a really excellent video on how to go about teaching yourself GR and resources you could use. He mentioned that, for example, one of the cons with Hartle is that you see, for example, stuff like the Einstein field equation all the way at the end of the book. Now, it can be a hypocrite because the same thing goes actually for covariant physics. You don't see the field equation still around chapter 7, but it's still the thing that I'd say covariant physics has over Hartle is that you get more quickly introduced to tensors and like tensor algebra and stuff like that. So really, if again, as I said, if you work through the first 2 chapters of covariant physics, you're very good to go. Whereas with Hartle, you get a nice, easy, you could say, segue into stuff. Like it's very easy, honestly, to read. But because of that, you don't get the stuff which you really need early on, and you might stop before you get to some of the more important stuff. But still, it is pretty good, and it covers, especially once it finally gets into it, it covers materials really well, like stuff regarding gravity waves and stuff like that. I remember it doing a pretty nice job at that. So do give it a shot, especially as like an introductory book into general relativity. Now, besides Hartle, the other GR book at the level of undergraduates I'd say that I really recommend is Anthony Z's Einstein's Gravity in a Nutshell. And this is, if you look at it physically, it is a big book, but it is a phenomenal book from the bits that I read. Like it really introduces both the physical intuition, which Hartle places emphasis on, as well as the mathematics early on, like covariant physics, blends those two good aspects together, and that sprinkled in with Anthony Z's amazing pedagogical writing. Like I think a lot of people who are especially furthermore into physics know Anthony Z because of his other textbooks, like his quantum field theory textbook and his group theory textbooks, amongst I'm sure many others. So he does a really nice job. From the bits that I read, for example, he even covers stuff like the 8ZM formalism of general relativity, so the Hamiltonian formalism of it, which is not something you see oftentimes done. So that was pretty interesting. And generally, this book is very complete. I'd say it is even better than Hartle if you want to have one GR book to kind of buy and kind of use to teach yourself this stuff. It also has a section on special relativity, so that is also really nice. So in general, I really like Anthony Z's like GR book, and I would heavily recommend it if, for example, you don't want to go for something like covariant physics, but was something that it has even more emphasis on, you could say, just pure GR, then go for that. I think it's the great first book, you could say, for learning general relativity. Lastly, the last book that I wanted to mention here is not basically a textbook, but not all of the books in this video will be textbooks, but things that you still can kind of learn from and make notes as if you were reading a textbook. And the last one for the easy books in GR is General Relativity, the Theoretical Minimum, written by Leonard Susskind and Andrei Caban. And this book right here is a phenomenal book, again, from the bits that I read. Because it's a Susskind theoretical minimum books, and these are usually really nice. Like he has one on quantum mechanics, on classical fields and special relativity, and classical mechanics as well. So all of these are really nice, and this was the most recent one that came out, and it's pretty good. Like he uses a lot of, you could say, approachable anecdotes and, you could say, thought experiments to kind of get you into the grooves of things. And the thing I like the most about the Susskind books are that they are very informal, especially. So when you read them, it reads very, you could say, in common language, you could say, and that is pretty nice because it makes the subject less intimidating, you could say, for someone reading it. Like you can read it, you can almost have fun with it, much like books written by Richard Feynman. So it is really, really nice, and I would definitely recommend this one. It easily eases you into notation, like tensor, you could say, notation, and what certain symbols means and stuff like that. He really tries to explain everything as best as he can. So I definitely think you'd have your bang for your buck by getting Susskind's book. Now, that was it for my GR easy books. Now, onto the cosmology easier books. And the first one that I would recommend for sure is Introduction to Cosmology, written by Barbara Ryden. Now, Barbara Ryden is an author which has an even more famous textbook, which is The Foundations of Astrophysics. And if you've read that, then you know roughly what to expect here as well. Basically, a very nice, relaxed approach towards introducing you to concepts in cosmology. The math is not too tedious either. Like, it's very, Barbara Ryden's books are very approachable, so it is nice for the absolute beginner, you could say, and it introduces you to what you need to know. Like, for example, I remember reading the bits on introducing co-moving coordinates and redshift and stuff like this. I remember those to be really actually well done, and it is also not a big book. It is, I remember, if I remember correctly, a very, you could say, thin book. So it is a nice thing to have in your collection. I personally am not quite a fan, mainly, well, for one, maybe there are two things, but there is more of a personal taste, so it's nothing on the book, honestly. But for one, for example, she has a sense of humor, which I like people, authors that have their own sense of humors, but hers just doesn't click for me. And two, also, the material is too surface level. Like, for me, it just leaves me wanting more. But I guess, again, if you're someone that is learning all of this for the very first time, then I think it might have a benefit for you to just have a surface skim through everything. So if I were to put myself in someone like that shoes, so someone learning this for the absolute first time, then I see no problem with Ryden's book. But there is another one which I think is slightly better than Ryden. Now, the other book recommendation I have for cosmology is An Introduction to Modern Astrophysics by, I think, Carol and Ostley. I forgot the first person's name, but Ostley is definitely the second one. And this is the big orange, you could say, Bible for astrophysics, and it's a great book. I've landed once personally, like when I was doing a project and I was reading on cataclysmic variables and compact binaries and binary star formation with things like the Roche lobes, etc. And it was just an incredible thing to read from. It was very fun. It was very complete, and generally it has almost every topic you can think of in astrophysics, including cosmology, which is why I'm recommending it here. The level at which I remember, because I did skim to the cosmology parts out of curiosity, the level at which I remember it covers it is at the level between Barbara Ryden and the book that I'm going to talk about after this one, and I find it to be a sweet spot. Like, it's a nice thing, especially if you get this book, that you'll get out of it. Like, it introduces cosmology fairly okay, and also just generally you have a book that talks about so many other topics. So it's an incredible book. It's very big though, so if you want to buy it physically, be aware of that. Like, it's a very, very, very big and heavy book, but it's a great one nonetheless. Now, the last easy, you could say, or easier introduction to cosmology book that I wanted to recommend is actually the one that I have by here, which is A Course in Cosmology, written by Dragan Hutterer. And this is a very new textbook. I actually lent it from my current thesis supervisor. It was in his office, and I asked him if I could like lend it, and he was like, "Okay, sure." And it was pretty nice because it helped me kind of recap some stuff from cosmology. Since when by the time I had started my thesis a couple of months ago, it had been like a year since I've done the cosmology course. So even though I am quite comfortable with the topics, there are some fine tuning details that I didn't remember. So there was a nice refresher. But generally, this book is really nice. It's one of the really good new textbooks. And the reason it's really good is because I honestly think it covers things with a little bit more depth than something like Barbara Ryden. But at the same time, it doesn't go too overboard. Like, what I mean by this is the contrast of these easier cosmology textbooks compared to every one of the other ones I'm going to talk about is that they don't necessarily care to show you too much of the general relativity behind it. Like, they don't show you stuff like Christoffel symbols, covariant derivatives, and stuff like that. They might hint at it, but they are not going to explicitly show you, even in an appendix, for example. They just go straight to what you need, basically, which is on the more cosmology side of things, which, believe it or not, is actually much simpler, or can be expressed in much simpler math compared to the thing in its full rigor. So this book is amazing for that. It introduces you to both things that are important for observational cosmology, as well as some of the stuff that is important for the theoretical edge of cosmology, and the excitement that this author shows in the open problems in many various facets of you could say cosmology, I think it makes it the perfect introductory textbook for cosmology. I really like it. Each section, for example, stuff like neutrino physics or inflationary cosmology or CMB anisotropies, are finished with a portion of the chapter dedicated to open problems, which again, fantastic, and also resources recommended at the end of each chapter if you want to go deeper into something. So great textbook, highly recommended. Now onto the intermediate level textbook. So the first intermediate level GR textbook that I have is of course none other than Space-Time and Geometry, written by Sean Carroll. Now this is not the first time that this book makes its appearance on this channel. Like I've talked about it before, especially in a book haul textbook video that I did, where I got this book for the first time and I was really excited to go through it. Now since then, of course, I have gone through bits of it, not in its full entirety. And as a matter of fact, I'm excited about it because for my master's course in GR, which is going to start sometime soon, this is the main book that the course uses. So I'm very excited to be working with this more frequently, like in about 2 months or so. But basically, this book is really nice at the stage where you've done the readings for some of those easier, you could say, GR books. And by the way, those easier GR books are good in their own respects as advanced treatments, but the thing that is good about Carroll is that he introduces the language of differential geometry very early on, and that makes a lot of modern treatments of GR much more accessible suddenly to you. Like you get to learn about stuff regarding manifolds, submanifolds, and differential forms and stuff like that. Now all of this is used in its full glory when talking about problems in general relativity and just descriptions in general. This book is a highly geometric book, and that is to say that if you're someone that likes doing algebra, he still does a lot of that, but he also ties the math a lot in with what you should visualize, which is really good for certain aspects, I think, or I feel, for GR, like especially when talking about killing vectors, which kind of preserve isometries, you could say, in a given space-time grid. But generally, for stuff like that and for just a more advanced treatment that is still very pedagogically accessible, it feels like Sean Carroll is the way to go. From bits that I read of it, it introduces stuff, for example, like Penrose diagrams really well, which is great for visualizing things like black holes and other funky, you could say, objects from GR, as well as laying the bedrock for just certain higher end applications and topics, like his chapters on black holes, his chapters on cosmology, especially I think one of the final chapters on quantum field theory and curved spacetimes. I think that was really nice. So generally, I definitely say this is the next book to get for the more intermediate and even advanced treatments of GR. Now, the next book I have in this category is one which I will put the disclaimer right now. I haven't used it that much, but from the bits that I have seen and from what I heard from others, it seems to be a really good addition to your library. Is a Relativist Toolkit written by Eric Poisson. And the reason this book is up here is it, for once, introduces you to aspects of general relativity and general relativity itself, but immediately with a higher, you could say, language for mathematics. So much like Sean Carroll, it spent its first 2 chapters or so, I think, introducing stuff regarding like Lie derivatives and more higher end, you could say, math tools that you could use then later in your GR calculations. And the strength of this textbook, from what it seems at least, is that it showcases various, you could say, topics of interest, you could say, in GR, and has dedicated chapters to them as to how to perform the calculations, and especially lays, like we could say, meticulously how to practically perform these calculations. So in essence, I don't think most steps are skipped here. So that may be a really nice thing to add, especially if, for example, you've already gotten the first treatment of GR and just wants to now hammer in on the little details. Next to Carol, this one might be also worthy of your consideration. I can't speak more of it because I don't know as much of it, but I just know that it's definitely one to put on here. Now, the last book I would put in this category is actually part of the Landau Lifshitz series, and that is Volume 2, The Classical Theory of Fields. And this book, there's a lot to say about it. Like, for the first part, I think people will be surprised, especially considering that the Landau series are known to be just hardcore and very intense and just not the most, you could say, accessible thing to get out there. But from what I've read everywhere, the second volume is the best one out of the series, like right next to the first volume, maybe. And the quantum mechanics I heard is pretty alright as well. But the classical fields is the one that has the strongest, you could say, recommendation. And even though I just recently got my own copy, I have started skimming it earlier on this year, especially when I went to CERN, like in the library. And it seemed like a pretty decent textbook. Now, mainly, I would imagine someone using this book, especially to give themselves a proper treatment of relativistic electrodynamics, so learning about the covariant formalism of the Maxwell equations and all that entails. But three chapters near the end of this book, like I think around chapter 11 to like 13 or 14 or something like that, he actually goes into GR because his main point is to go through special and general relativity, as especially GR is a more classical field theory, and he introduces it from what I saw really nicely. Like the notation is quite modern, and some of the calculations, especially for gravitational waves, I saw seems to be quite intriguing here. So I definitely say it's worthy of your look, even though it's just three chapters dedicated to GR. So Landau Lifshitz. Now on to the cosmology intermediate books. Now the first one I have here is Cosmology, written by Daniel Baumann, and Daniel Baumann is a phenomenal, you could say, pedagogical writer. Now, even though this book itself is one that I have not, you could say, used in its entirety, I have used Daniel Baumann's lecture notes, which is just extremely clear and so beautiful. Like especially his part 3, like Cambridge lecture notes on cosmology. I've used it to quite a lot of extent, even in my thesis. And he carries on that same element, it seems, in his book. And the reason this book falls in the intermediate place is because it does have some of that GR, you could say, lingo to it. Now, the chapters themselves are not fully dedicated to kind of go over GR in its entireties. That's why there are appendices in this book for it. But it definitely doesn't shy away from saying that, okay, if you really formally, for example, want to get the Klein-Gordon equations for like scalar fields or whatever, or if you really formally want to know something like the stress energy tensor for certain cosmological substances, then you ought to kind of tackle this rigorously through some GR steps. But this book is serving in the middle of the easier books like Corydon and some other ones to the more hardcore books, which we're going to talk about later. So it serves as the sweet spot in the middle, and that's why I think definitely I ought to mention and recommend it here. Now, the second book that is in the intermediate, you could say, level for cosmology is one called Principles of Physical Cosmology, written by Jim Peebles. Now, a book of Jim Peebles was also mentioned in my previous, you could say, book recommendation video for cosmology. That is the Cosmology Century book, and this one is more or less more like a textbook than that one. So this one is a very big book from what I saw, but it introduces every topic in cosmology and introduces them nicely, both things regarding observational aspects of cosmology as well as the more theoretical aspects of it. And he also mentions why these things are important and what are the relevance of some of the open questions. So in a sense of the way, the reason I'm recommending is because it's much like the Hutterer book that I talked about previously, that kind of it introduces various aspects of cosmology for you and kind of has the open questions right in there for you to look at, but it does so at a higher level. So that's why I would definitely recommend it. But now onto the good stuff. Now let's go on to the more advanced, you could say, level textbooks. And this is going to be really fun. Like these were very obvious picks for me, but still it's going to be really fun to go through them. So for GR, the first one and the one that I like the most so far for looking through, is the book Gravitation and Cosmology, written by Steven Weinberg. Now, this book is not one that you get to easily like a physical copy of because it's quite expensive if you look online. Like, it's an expensive book to get, but I had it because my academic advisor has this textbook and he's quite a fond, you could say, user of this book. And I needed to read up on the Platini, you could say, theorem for like the Christoffel symbol, and this was perfectly explained by Weinberg. And just generally speaking, Weinberg does a lot of really nice treatments for GR. Like, he is very algebraically oriented, so he goes through calculations meticulously. No stones are left unturned, and that is pretty nice, especially depending on who you are. But for me, that's really nice because it's consistent. It shows you the step that he goes through. And even on the historical side of things, he talks about some of the history of things, like in the introduction, for example, of this book. He was talking about about the history regarding discovery of non-Euclidean geometry, like the mathematicians that worked on this. He covered it in a breadth of work, which, as far as I've read, I haven't seen like in as many places. Like he talked about Levi Civita, he talked about Nikolai, and I think there's another person, but I forgot like his name right now. And of course Riemann, and how all of these people kind of were hammering on at ideas of non-Euclidean geometry, which kind of laid this revolutionary way of thinking in mathematics that hadn't come to be since the days of Euclid. And it's phenomenal to see his historical treatments and the breadth at which he covered things, and eventually went on to the GR side of things. And it's a great book, basically. So I definitely would recommend it if you can get a cheap copy of it, or if you can find it somewhere online, especially at the advanced level treatment. Like, it's not an easy book that you pick up and go through, but it is definitely one that it seems like you'd pick up if you want to see a calculation done very meticulously right. So Stephen Weinberg, definitely would recommend it. Another book that falls into this category, which I have limited experience with, again, is the book by Misner, Thorne, and Wheeler, and that is Gravitation, also called the Telephone Book or the Big Black Book of Gravitation, or just shortly MTW, like the initials of the authors. So MTW is a well-known and well-respected book in the community of gravitational physics because it just looks very fancy, and honestly, just for that is a reason that I maybe in the future might want to get it. It's such a big book and looks really nice, but also it is very complete and thorough. It is a book that has everything from special relativity in the beginning to, of course, GR and all of the elements that GR entails. And as a matter of fact, this book is so condensed and complete that I would even say that it is more like a reference textbook than it is a textbook you learn from. Much like, for example, when I in the past talked about the mathematical methods book, and many of these types of videos about book recommendations for physics books talk about the maths methods book that everybody knows about, either Arfken or the one that I have. Well, the thing is that these books, even though you can learn from them, I might not be the best thing to learn from them. And especially, for example, in the case of GR with Gravitation from this book, because it does at least read at times like it was written by three different people. So that might not be the best thing, especially if you're looking for style and consistency. But the book does have its strength. Like, for example, again, the breadth of topics covered is amazing. Like, it even covers stuff like the null energy conditions and stuff like that really well, and even has a great bit on closed time-like curves, which I may mention in a video that I am planning on making soon. So that is really nice, but generally this book is very complete. It does feel a little bit disconjointed a couple of times, but it is the perfect, it seems, reference textbook for like GR. Now, the next book recommendation I have is not one that I've personally honestly gone through almost at all, honestly, but I will still justify why I'm recommending it, and that is General Relativity by Wald. And this seems to be like another one of those like iconic, you could say, general relativity textbooks that people always seem to be talking about because it seems to be so good. And the main reason, or the main places I've heard about this is, for example, by that video of the Science Asylum again, by videos of Mark Weisman like recommending GR, and also by another video of this YouTuber, something O'Reilly. I don't remember his name unfortunately really well, but these people talk about this book. So if you want to get more of a perspective on someone who has gone through this book, go through any of these three videos. But it seems like Walt is good, especially again for doing practical, you could say, calculations from GR. So much like Weinberg and to some extent I'd guess MTW, this book is good especially for that. And the last book recommendation that I have is also one that I have very limited to almost none experience with, but I still mention it, is The Large Scale Structure of Space and Time, written by Stephen Hawking. What I will say about this book is that this is a mathematical physics textbook, and I think it is important to emphasize that, because mathematical physics and theoretical physics to some may seem like the same thing, but they're really not the same thing. They're two different beasts. Like, the mathematical physicists typically very much care about rigor and formalism much more so than a theorist would. So the theorist will be fine, for example, making certain assumption and not worrying exactly where certain mathematical things come from, but as long as they can use it for their intents, for their purposes, whatever those may be. Whereas the mathematical physicist cares about, he is a mathematical physicist, he or she is basically a mathematician by training. So they care about having theorems, lemmas, and having things logically follow from the other. And that kind of very much is front and center in this classical, you could say, book about GR, this Stephen Hawking and Alice book. The Large Scale Structures of Space and Time is a book that covers many topics, it seems, from general relativity, but again, with a lot of rigor. So it is not the lightest read, and also it might not be actually a very preferable read for most people, like depending on who you are. Like I know for personally for me, it's too much rigor, but again, so if someone is from a more mathematical background, then definitely go for it. And mathematical, I really mean like a mathematics background, like not just someone that is really comfortable with applied mathematics, because it does seem to do some things at least really right. Especially, I remember seeing like a whole chapter dedicated to causality in general relativity and all the things that entails, and that seems to be covered quite rigorously with talking about the Cauchy horizon and the submanifolds that are entailed in there. It seems to cover that very thoroughly, and Sean Carroll does so as well. It's one of the first bits of Sean Carroll that I really like, but it seems like this one really flashes this out and really gives examples of places also where GR breaks down, like at both, for example, past the Cauchy horizon, so past especially singularities, and also in solutions to the field equations that give you closed time-like curves. So, and indeed, they actually explicitly go through the Gödel metric, which is a famous example where general relativity breaks down and you have solutions that have closed time-like curves. So basically, it allows you to travel backwards in time. So phenomenal stuff if you're the right audience basically for this book. So that was it basically for my GR advanced textbook recommendations. Now let's go on to the cosmology ones. So for cosmology, the first textbook recommendation I have is one called Modern Cosmology by someone whose name starts with D. I always mess up his name, unfortunately, but the reason I'm recommending the textbook is because it seems to be much like the Jim Peebles intermediate book, the physical principles in or principles in physical cosmology book. It seems to cover a lot of those same topics, but even with more careful treatment. Like, for example, especially I feel like if someone wants to get into observational cosmology, this seems like a really good book to maybe have a look at. Because, for example, he even covers some of the statistical methods used in like analysis for cosmology. Like, this is one of the few books I saw that has a very, you could say, thorough chapters on Fisher matrix analysis, which is a common trick of the trade, you could say, for doing gravitational and cosmological physics. So that seems to be very wonderfully done there, although I have not seen a lot of people's opinion on this book, so I also don't have much to say because it's not one that I've used personally that much, but it does seem to be good for what its intended use is. But the last book recommendation I have in this section is one that I have worked through quite at least some portions of it, and I really, really love it, and you can take a guess as to which one that is. Your guess may be right, and even especially as the video kind of cut and you might not see it there anymore, it is Cosmology, written by Steven Weinberg. Now again, there's a pattern there. It seems like I really like Weinberg's textbook. Now, there is a con with Weinberg's textbook that I did not mention with Gravitation and Cosmology, but definitely I will mention here because it especially applies to this one. But the main thing I really like about this book is, again, same thing I like with Gravitation and Cosmology. Very thorough. The calculations are done meticulously, and like I've used it quite a lot. Like you can see my paper is kind of stuck in there, but that doesn't justify things because like I've went all over the place with bits of this book. I like it so much because, for example, the bits on inflation that he covers them thoroughly. The cosmological perturbation theory is also done really nicely in this book, and even stuff regarding the Big Bang nucleosynthesis seems to be covered with nice care and detail. And the first chapter also introduces you to some of the tools you need to start thinking in terms of cosmology really well. Now, the GR terms, like the GR basically is left for mainly the appendix here. Not to say that he doesn't do GR calculations in the book, like throughout the book, contrary to the intermediate level books, which mainly hint at it in something like Bowman. Oh no, he really does the GR calculations. Like, for example, instead of saying that something like a pressureless fluid for the case of cosmology, that it has a stress energy energy tensor with main diagonal elements or something like that, he actually shows you where like these elements from the stress energy tensor come from, calculates the Christophers rigorously, and like he does everything by first principles, and it's amazing, thorough and carefully detailed. But the reason I said that the GR is not the main focus of this book is even though it does the calculations thoroughly and has a good appendix section on refreshers of things from GR, it is not gravitation and cosmology in the sense that it looks at other applications of GR like gravitational waves or black holes. Like this one is a mainly, as the book suggests, a cosmology book. And he came with it, from what I heard, this book came out, I think, by the way, in the early 2010s, so it's relatively recent. He came up with it because he needed to take a sabbatical or something like that, and it seemed like he wanted to use his time to learn something new, and he thought, why not look into the recent advancements in cosmology? And that's what makes this book really interesting, because, for example, in contrary to gravitation and cosmology that came out in the 80s or 70s or so, I think 80s, this one is more modern, and that is good because cosmology is a field that has changed quite a bit, like ever since the 80s. So it is a really nice, modern, you could say, thing that someone that especially wants to get into cosmology could reference. Now, this one, even though he talks about observations, it's very focused on theory, which is, I guess, why I personally like it a lot. So it depends on who you are. But the con that I have with Weinberg sometimes is that his notation is very inconsistent from that of other sources, and that makes it sometimes quite annoying to read, because if you're reading something and you want to understand it from not just Weinberg but other people as well, then you may go to other sources and be very confused because you're like, where is this new term coming from? Whereas I saw it in Weinberg, it seems to be something else. But the problem is that Weinberg, he likes teaching himself when especially writing these textbooks, so he would do everything himself, and because of that, he makes up his own notation. And in a time and era at which notation is already bad in physics, this just makes things sometimes quite a mental gymnastics to kind of make the connection between two different sources. But the physics is still good, and that's why I am still heavily recommending this book. Now, in principle, that was it for the specific textbook recommendations, but I did want to give some notable mentions, some notable textbook out there that might be worth your time. And to start off, the first, you could say, notable mention is if you're, again, more of a mathematical physicist person, so maybe you like stuff like the Stephen Hawking book, then you may like the book A Mathematical Theory of Black Holes, written by Chandrasekhar. And Chandrasekhar is a very noteworthy astrophysicist that worked especially on white dwarfs. He came up with the idea of electron degeneracy being the way that white dwarfs can retain their stability, and just generally he has some amazing resources, it seems, for astrophysics, even especially stellar astrophysics. But this book that I'm talking about, A Mathematical Theory of Black Holes, is a book that dives nicely into GR and especially its use in things regarding black holes. Now, from the bits that I saw, it does seem to be, again, very much a mathematical physicist book, where in the sense that the first chapters seem to be mainly dedicated especially to introducing a lot of the fancier, you could say, math that is needed to work with GR at the highest level. So again, depending on who you are, this may benefit you, but just do keep in mind, very rigorous. The other book that I wanted to talk about is one called Black Holes, White Dwarfs, and Neutron Stars, written by Teokalski, I think. And this is a book that mainly focuses on the subjects of its title. It is a book about compact objects and seems like a very nice book for especially people that want to work in this field, because even though it shows how general relativity can be applied in studying these objects, it also especially hammers on the astronomical details of them. So stuff like the light curves you'd see from them, or the astroparticle physics, so the particles that would be emitted from them and stuff like that. So it kind of really makes this really good connection between theory and observation, which is great, especially if you're trying to study these objects in the sky. So that also seems like a phenomenal textbook. Another, not per se textbook, but more or less book that I wanted to kind of give a pointer at is this book, which is The Essential Einstein, His Work and Such, written by Stephen Hawking. And I got this book when I went to Paris like about 2 years or so ago, and it's a really nice book. It covers stuff from Brownian motion, special relativity, general relativity really nicely, and of course it's kind of directly from the person. Like it's kind of summarizing papers that Einstein wrote, and Hawking does a good job at this. Like it's not a terse thing to read like the large scale structures of space time. Like it is much more even clear. Like I think even if you look at, for example, the original papers that Einstein wrote, you'd be surprised as to how clear they are to follow. Like some old papers are actually really nice to go through if you give it a shot. So this one does a really nice job highlighting the stuff that Einstein worked on, and I really like it for that. It's like a nice, you could say, historical memorabilia that you can kind of buy to go through if you wanted to see how Einstein himself thought about these things. So definitely would recommend it. The next book that I wanted to recommend is Feynman's Lecture on Gravitation, written by some of his students, and this is a collection of notes from a course that Feynman taught, and it's a book of related to GR, written by Richard Feynman, which of course is pretty interesting always. Now, this book is quite interesting because it is not per se just a course on general relativity, but it is mainly a book about how Feynman tackled some of the problems of quantum gravity, since this is something that Feynman worked for at least a portion of his life on, and it's quite interesting because Feynman basically applied you could say, the same techniques that worked for him when tackling problems of quantum electrodynamics to the problem of gravity. And he seemed to have gotten quite a bit of steps in there, but because this is a much harder problem, he didn't manage to go all the way in there. So it is interesting because in this book, he kind of outlines some of the issues with trying to quantize gravity, and also he shows examples. Like he shows examples of, and you can kind of see the way he thinks, which is amazing. It is phenomenal, like how he grabs very conservative ideas, stuff that we know worked, and just apply them and see what comes out of it. For example, by thinking in terms of, for example, if I have the star and two, you could say, planetary bodies, and if I make their distances large enough, then what would the mediator between these two objects be to cause some sort of attraction between them? And he makes guesses with, like, oh, could it be a neutrino that is the exchange particle? What happens if we assume it is? And how does this affect, you could say, the scattering amplitude calculations and the rigorous, you could say, QFT that you need to do? It's amazing. It is explained so nicely by Feynman. Of course, Feynman isn't always the best, you could say, when it comes to his explanations and writing. Even though he's the great explainer, the reason I'm saying this is because, for example, if you want for the first time to learn something, he's not always accessible. But if you want to understand something, then he's amazing. Very informal, much like Susskind, which I love. So it's really nice to go through for certain aspects and also for historical reasons. So some things are a bit old-fashioned here, especially his thoughts on cosmology. But generally, this is a really nice book, especially to see how you can still get a lot of the things that you'd get from GR out of there, from basically principles of like working at it from like a more quantum field theory approach. And also it's the place, Feynman's theory is the place where the idea of gravity being mediated by a spin 2 boson kind of really started coming out of. And it's this thing which people still speculate if whether or not it may be a part of the standard model, the spin 2 boson called the graviton. So it's a really interesting book and might be definitely worth your time, especially if A, you like Feynman, and B, you want to have like this historical context of ways people worked at quantum gravity. Now, the final book I'm going to recommend in this video as a noteworthy mention is a book called Lorentzian Wormholes, written by Matt Visser. Now, this book has several things going on for it, which I really like, and it is a book about traversable wormholes, so that already is really fun. So if you like stuff, especially from science fiction ideas like Interstellar or other, you could say, sci-fi stories, then this may definitely appeal to you. And the other thing is Matt Visser is hilarious. Like his sense of humor, I think compared to someone like Barbara Ryden, I absolutely love it. It is not dry humor by any sense. It is sarcastic humor. It is amazing. I think you should just read the preview of this book, like the first like preface of it in the preview. You get exactly what I mean. I actually found myself laughing quite a bit where I was reading the book because he's genuinely really funny. And also this seems to be the authoritative book on the subject of wormholes. So if you, again, really like the applications of GR that gives you wormholes, this seems to be a great one to go for. And it's interesting for many reasons. Like, for example, if you're someone who's always, if if the sci-fi thing that always kept you up is the idea of time travel, especially time travel to the past, then exploring a topic such as traversable wormholes really scratches that itch that you want in terms of thinking about how one could scientifically imagine time traveling. So I think, for example, if you want a serious book on physics that kind of explore ideas related to time travel, then I think definitely look no more further than Lorentzian wormholes. It seems to be the one that does the trick. The chapters are really short. I haven't gone through the whole thing, of course, by the way, but from the bit that I have read, phenomenal, and I can't wait to just to go in through it a little bit more. And it seems like one that after even an easy or intermediate treatment, I'd say even if after, like you say, an easy treatment of GR, you could attempt to first to start reading it. Now there are things which you might not fully get and that I also do not fully get, because it does refer to things regarding manifolds, topologies, and especially quantum field theory and curved space-time topics. He even introduces that, by the way, in here, so that's also really nice. But that someone like you and me might not get immediately, but it still seems like a very approachable textbook. So I could not leave that out in a video talking about general relativity textbook. So definitely I'd say would recommend this, if not for anything, for this guy's sense of humor. It's so underrated. It should be talked about more. It's incredible. So that was it for my textbook recommendations, or my serious book recommendations, basically for general relativity and cosmology. I hope you enjoyed them. I know certainly that I do enjoy a lot of these books. And if you have some recommendations of your own, please feel free to leave them down in the comment section down below. I think some people will definitely benefit from this, as everyone's looking for some good GR cosmology textbook. And I just thought, why not join the party? Because I also kind of like these topics. So yeah, I hope you're going to have a good day, and I hope to see you all very soon in more videos. Bye bye.